All right, in this video, we're going to work an example problem related to finding the amount of work done for a certain situation. And so we're talking about work in the sense of like from physics, mechanical work, force times distance. And so this application of integration that we're studying, it's not so much about work as it is, this is an example of a real world application that is being applied to integration. And the idea is, so work is a force acting over a distance, a force on an object that acts over a distance that object moves. That's work. That means that's the work done on the object. And so to calculate the amount of work done on an object, we thought about the idea of, well, if you break down the distances that the object moves, so if you have the position function of an object, the position with respect to time, then you can think about if it goes from one position to another position, then that's like a displacement. That's the amount the object moved. And so if we break down that position function, the position being like an independent variable, into equal width pieces, so the entire change in position, the entire displacement, if we break that down into equal width pieces, and if those pieces, the width of those pieces is small enough, then we can assume that the force that acts over that small displacement is constant. And then for that little interval, we can multiply that constant force times the displacement to get a work done for that little interval. And then we add up all the intervals to get the total work done. Okay, and so thinking about it this way, what you realize is that, well, that's the exact thing we do with integration. When we developed the concept of integration, that's exactly what we were doing. We had an area under a curve that we wanted to calculate. And we broke up the independent variable into these equal width pieces. And then for each piece, we assumed that the height of the curve over that interval was constant. And then we calculate the area to be the width of the piece times that height. And so that's why, if you think about, so you know the position of an object with respect to time, let's say, and then from there you can think about, you would express the force acting on an object as a function of position. And so if this was the force, the dependent variable was force, and this was x, the position, then any delta x would be a change in position. So it's a distance the object moves, and so over that small distance, if these pieces get large, you assume that the force is constant over that small change in displacement. That's a work done. That's the definition of work. And so you can see how we're applying a real world physical phenomena, force times a distance, and using the idea that if we happen to have a variable force, a non-constant force, we can use the concept of integration to find the net force times distance, the net work. So again, the main purpose of this section on showing us how using this example of calculating work done and from a physics sense is just showing you how you can take something you're trying to solve for in any subject, biology, chemistry, engineering, and a lot of problems you can solve for something using integration. So this problem says a leaky 10 kilogram bucket is lifted from the ground to a height of 12 meters at a constant speed with a rope that weighs 0.8 kilograms per meter. Initially, the bucket contains 36 kilograms of water, but the water leaks at a constant rate and finishes draining just as the bucket reaches the 12-meter level. How much work is done? All right, so here's the ground. The bucket is 10 kilograms, and it initially contains 36 kilograms of water. So I guess we can imagine like a roller is lifting the bucket up. Okay, it's a leaky bucket. And so let's say you're trying to lift the bucket to, this is 10 or 12 meters. So the bucket, the mass of the bucket is 10 kilograms. All right, the rope weighs 0.8 kilograms per meter. And I guess we'll say that this is, let's just call this X. That's the height of the bucket. Starts at 0 and it's going to 12. All right. Now it's saying constant speed. This is really simplified, physics problem just for the sake of showing how the calculus works. Like, it's constant speed because otherwise then the force would change. But if it's constant speed, then we're just considering the weight of the bucket. This is like straight line motion, so the force, the weight, the weight, the force is the weight of the bucket, and that's in line with the displacement of the bucket. Well, I mean, this is actually kind of realistic if you're lifting a bucket like that, but it's still very simplified physics problem for the sake of just illustrating the calculus. So, all right. The rope weighs 0.8 kilograms per meter. Initially, the bucket contains 36 kilograms of water, but the water leaks at a constant rate and finishes draining just as the bucket reaches the 12-meter level. So, okay, I mean, let's just start with we can get the weight of the bucket as a function of x. Let's do that. So, all right, the water leaks at a constant rate, so it's going to be linear. And so, all right. The weight of the bucket as a function of x is, when at x is equal to 0, the bucket is the 10 kilograms plus the 36 kilograms, so 46 kilograms, 46 times 9.81. $451.3. Okay, so 451.3 newtons, but then minus, and so it's going to, you're going from x is equal to 0 to x is equal to 12, and you're subtracting out. When x gets to 12, what you end up with is the 36 kilograms. So 36 times 9.81, $353.2. So 353.2 divided by 12x. That should be right. Because the idea is when x gets to 12, then you're subtracting out this 36 kilograms of weight. When x is 0, you're not subtracting out any of the weight. And then it's just when x is between 0 and 12, then you're subtracting out a portion of this weight. You see? So let's take 353.2 divided by 12. $29.4. Yeah, so there you go. That's the weight of the bucket as a function of position. And again, this is very simplified. How would you know I guess you would know the position of the bucket as a function of time. You don't get bogged down with thinking, oh, this is so unrealistic. How would you know this? If this is just for illustration of the calculus. I guess you'd know the position of the bucket as a function of time, and then you have a sense for, I guess you could, if you knew the position of the bucket as a function of time, and you know that the bucket leaked all the water when it got to the top, I guess this isn't that unrealistic. All right, but that's the weight of the bucket as a function of x, of its position. Okay, but wait, though. So this is, I want to put here weight of bucket, because this isn't the total force we're dealing with. They're asking for the work required to lift like the bucket and the rope. So what's the weight of the rope as a function of x? So the weight of the rope as a function of x is what? The rope weighs 0.8 kilograms per meter. So when x is equal to 0, you've got 12 meters of rope. And the way I drew this, it's not, x would be at the bottom of the, right? So, let me just try and make it as realistic as I can. So it would be kind of like that. Something like that. The idea is we're pulling in 12 meters of rope, and we're also going to lift the bucket 12 meters, okay? So with 12 meters of rope at 0.8 kilograms per meter is 9.6 kilograms, and then now we multiply that times 9.81, 94.2. So we start out at 94.2 when x is equal to 0, and then from there we're subtracting out 0.8x, right? Because that's how much rope has, as x goes up, that's how much rope has been pulled in and is no longer a part of the weight, right? So like when we get to 12 meters, what's 0.8 times 12? 9.6. Oh, wait, no, but we need to multiply 0.8 times 9.81. 7.8, because that's the mass of the rope. We want to convert this to newtons per meter. So 7.8x. Okay. So therefore, the weight that we're dealing with, like the actual force that we're going to be calculating the work with, we're going to be calculating the force over a distance, is going to be weight bucket plus weight rope. So 451.3 plus 94.2. $545.5. Okay, now 29.4 and 7.8. Then minus 37.2x. So that's the force function as a function of position. And so what we want to do is to calculate the work done, we want to integrate this. So we want to break up these change in x, like, so we want to break up the x, the independent variable here, into these pieces to where you get these small displacements, these small distances that the bucket moved. And they're so small that we can assume the force is constant over that distance, that displacement. And so then we can say that force times that small displacement, and then we add all of those pieces up. Those are like little work pieces. Well, that's exactly what integration would be in this case. That's exactly what, if we integrated this w of x dx from 0 to 12, that's what it would be. So the work done is you go from 0 to 12. Okay. So this is 545.5x minus then 37.2 divided by 2. 18.6 x squared. Integrate that from 0 to 12. So 545.5 times 12 minus 18.6 times 12 squared is 144. 3868. This is Newton meters, so this is joules.